Good afternoon, all of you. In the previous class, we studied about measurement of internal energy change and of enthalpy change in a system. So we used calorimetric methods for that. And towards the end of the class, we spoke about another term, which is heat of reaction or enthalpy of reaction. So continuing that, we will be studying more about enthalpy of reaction in this class. So enthalpy change, which was represented by delta RH of a reaction. Reaction enthalpy. So the enthalpy change accompanying a reaction is called reaction enthalpy. Whatever change or energy change or heat change which is happening while carrying out a reaction is known as enthalpy of reaction. The enthalpy change of a chemical reaction is given by the symbol delta RH. All these facts you know. So if we consider a reaction, a usual format of a reaction is reactants giving products. So both of this, the reactant and product, will have an enthalpy value. Reactants together they will have an enthalpy value, and products together they will have an enthalpy value. So difference between these two will be the enthalpy of that reaction. So that will be the enthalpy change which is carried out in a reaction. That is also obvious. If we want to measure the difference between two things, what we do? We just subtract one of them from the other one. Then we can understand what is the difference between them. So similar in this case also, if we need to find out the enthalpy change between reactants and products, which is delta RH, then we need to subtract one of them from the other. So the equation to find out the enthalpy of a reaction is delta RH is equal to sum of enthalpies of products. So in reactant side and product side, we have not just one of a compound on one molecule, we have a lot of compounds and lot of molecules in both the sides. So sum of enthalpies of all the products what we get minus the sum of enthalpies of all the reactants. That when we do, we get the difference between them or the enthalpy of this particular reaction. We will see an example. So CH4 plus 2O2 gives CO2 plus 2H2O. This is the reaction. And in that, in both the sides, we have two reactants and two products. So applying the equation delta RH is equal to sum of enthalpies of products minus sum of enthalpies of reactants. A chemical reaction not only gives us an idea about what is inside, it also gives us an idea about how much, or it gives us an idea about what is the quantity which is reacted. So if we consider this as a molar equation, 1 mole of CH4 is reacting with 2 moles of O2 gives CO2 1 mole plus 2 H2O. So the moles also are represented, or the quantity is also represented by a chemical equation. And this quantity is also important in case of enthalpy. For example, if I take 1 kilogram of coal and if I burn it, the amount of heat which is produced will be different from the quantity if I reduce to 1 gram and if I burn it, both the enthalpies will be different. 1 kilogram of coal will give a higher heat energy than that of 1 gram of coal. So enthalpy also is dependent on the amount of substance we take. So here also we can alter this equation slightly and write it like this. The same equation we are writing, but here you can see one more term which is the stoichiometric constant. So AT, here it represents the number of moles or whatever it is. So number or the quantity is represented by this stoichiometric coefficient here in both the sides. So first we multiply the stoichiometric coefficient with the enthalpy, then we sum it and apply in this equation. For example, here what we do, the product side. So the number of coefficient, here there is no coefficient. So the enthalpy of CO2 plus 2 into enthalpy of H2O minus this minus, then comes the reactants. 2 into enthalpy of oxygen plus enthalpy of CH4. Like that we can write it. Now we will actually write it. So applying this equation, the molar enthalpy, as it is a molar equation, we are considering the molar enthalpy. So molar enthalpy of CO2 plus the 2 into the stoichiometric coefficient 2 into molar enthalpy of H2O, that we will sum together. We will take the summation minus, now comes the reactants, the molar enthalpy of CH4 plus 2 the stoichiometric coefficient into molar enthalpy of oxygen. This will gives us the enthalpy change of this reaction, or the enthalpy of reaction of this particular reaction. HM is the molar enthalpy, so that we have told. And now we will see why we are doing this, why we need to find out this enthalpy change of a reaction. So we will see why it is done. So knowledge of this quantity or this enthalpy of reaction is required when one needs to plan the heating or cooling required to maintain an industrial chemical reaction at constant temperature. So when we know that this much of enthalpy is going to be exchanged in between reactants and products, we can maintain industrial conditions like making it constant or the reaction temperature to make it constant. All those things we actually need to find out the enthalpy of reaction. So once we know how much energy is exchanged, we can provide or we can absorb the energy and make them constant. It is also required to calculate the temperature dependence of equilibrium constant. So equilibrium constant also, in that also we need to find out the enthalpy of reaction. Then with the calculation we need to find out how much energy is needed and or to be liberated from that. So all this are the needs of finding out the enthalpy of reaction. And more about this equilibrium constant and all you will learn in the chapter equilibrium. So now we are moving on to the next topic, which is standard enthalpy of reaction. So we have learnt about standard measures in the chapter states of matter. So it is somewhat similar to that. So enthalpy of a reaction depends on the conditions under which the reactions are carried out. I told that enthalpy of a reaction is not constant always. So it will vary according to conditions, like if we change the pressure, if we change the temperature, heat, etc. So that might vary, or if the quantity changes, there are a lot of conditions we can apply to a reaction. So in that case, we will have a lot of data for each and every reaction. Like in this particular temperature, at this particular pressure, this reaction is carried out, then we will get this much of enthalpy. Like we have vast amount of data for each reaction. So to reduce that, we have a system or a standard system of enthalpy. At this system, we can tell easily the conditions. So similar to that, we have told in STP for states of matter. States of matter reactions we told in STP, standard, temperature and pressure. So similar to that, we have standard conditions for enthalpy of reaction also. So it is necessary to specify some standard conditions in this scenario. So the standard enthalpy of reaction does not tell like STP. So it is enthalpy change for a reaction when all the participating substances are in standard states. So what is this standard state? That is what we are going to think now. The standard state of a substance is at specified temperature is its pure form at 1 bar. So that is the condition here. If we tell that one reactant or product or the reaction is in standard form, then we can tell it is under 1 bar and it is at the completely pure form. Or we can tell there will not be any impurity which is present. So without any impurity at 1 bar pressure, we can tell that particular substance is at standard state. So standard state means that at pure form it should be in 1 bar pressure. That is the standard state. We are not mentioning the temperature here. Usually like STP we mention temperature also, but in this case we don't mention temperature, but usually it is almost around 298 Kelvin. But sometimes it changes, so we can't tell that. Just concerned about the pure form and 1 bar pressure. So standard state of liquid ethanol at 298 Kelvin is pure liquid ethanol at 1 bar. So this is an example for a standard state of a substance. Standard state of liquid ethanol, we sometimes mention this temperature, but without mentioning also we can tell it's a standard state. So standard state of liquid ethanol at 298 Kelvin is the pure liquid of ethanol at 1 bar. So that is important. Pure liquid of ethanol without any impurity at 1 bar pressure. Then we can tell it is in the standard state. Another example, standard state of solid iron at 500 Kelvin is the pure iron at 1 bar. So pure iron at 1 bar pressure is the standard condition. Here you can see the temperature changed. But we can tell it's a standard condition because it's a pure iron at 1 bar pressure. So usually the data are taken in 298 Kelvin, but we can't tell it's a sure thing. Here you can see it might change also. Standard conditions are denoted by adding the superscript, which is this symbol. So this symbol, if you see, you can understand that it's a proper standard condition. For example, we can write the delta H like this. So delta H as a superscript, we will give this symbol. Then we can understand it is in the standard condition. So we studied about reaction enthalpy and standard enthalpy conditions. So now we will be studying about enthalpy in different processes of nature. So first is enthalpy changes during phase transformation. Here the phase transformation tells us about change in state. For example, like solid state to liquid state back to solid. All this is being mentioned here. And what is the enthalpy change happening during that phase transformation? That's what we are going to discuss now. So phase transformation always involve energy changes. For example, if ice is in the solid state, that ice when it changes to liquid state or water, it needs heat energy. So when we provide heat to ice, then only it will change to water. So that is a phase change and that requires energy. Similarly, almost every phase change requires energy or it gives out energy. So we will be studying about the enthalpy changes happening in this kind of phase changes. So we have classified it to three types, which are enthalpy of fusion. So enthalpy of fusion is carried out when a solid is changed to liquid. So enthalpy of vaporization is when a liquid changes to gaseous state, and enthalpy of sublimation is a different case when the sublimation happens or when the solid directly changes to gas. So these are the three conditions which we have to measure the enthalpy change. First we will deal with enthalpy of fusion. So in enthalpy of fusion, the change is from the solid state to liquid state, or we can take the example of ice to water. So water at the solid state, which is ice, gives water at liquid state. So that time the delta fusion H, this symbol is for the standard state as we know. So at standard state, enthalpy change of fusion is 6 kilojoule per mole in ice. So it needs 6 kilojoules per mole of energy at standard state to change from H2O solid to liquid. So that is the enthalpy of fusion at standard state. If water freezes, which means this process is reversing, the water coming back to solid state, then the process is reversed and the equal amount of energy has to be given off to surroundings. So once the heat is absorbed by the ice, it turns to liquid, and when in reverse process, the liquid gives out energy and then transferred to solid state. So the same amount of energy is being used in both the cases. If it is coming from solid to liquid, then energy is absorbed. 6 kilojoules per mole of energy is being absorbed. If it is returning, 6 kilojoules also is being given out to surroundings and forms ice. So the enthalpy change that accompanies melting of 1 mole of solid substance is the standard state is called standard enthalpy of fusion and molar enthalpy of fusion. And there we have the definition for molar enthalpy of fusion. So enthalpy change when 1 mole of a solid or ice melt to form water. That particular enthalpy change is known as enthalpy of fusion or molar enthalpy of fusion. So melting of solid is always endothermic. It absorbs energy or heat energy and then melt. So all enthalpies of fusion are positive. As the system is gaining energy, enthalpy of fusion is positive. Next is enthalpy of vaporization. So similar to that we told in case of enthalpy of fusion, enthalpy of vaporization is when the liquid changes to gaseous form. So H2O liquid forming H2O gaseous form, the delta vaporization will be equal to 40.79 kilojoules per mole. So in a mole, if 1 mole of liquid is converted to H2O gas or water vapor, it needs 40.79 kilojoules of enthalpy or energy. So that at standard value or standard state, it is known as standard enthalpy of vaporization. So amount of heat required to vaporize 1 mole of liquid at constant temperature and at standard conditions, it is called the standard enthalpy of vaporization. So when it is in a mole, it is told as molar enthalpy of vaporization. So when we told about the solid to liquid form, we told as the enthalpy of fusion. In this case, we are telling it as enthalpy of vaporization. So as it is from liquid to gaseous, there is the only change. But both the cases, it is the energy required for the state change or phase transformation. Next is the enthalpy of sublimation. I hope you all know about what is sublimation. So sublimation is a process where a solid is directly converted to gaseous form. It does not come to liquid state. In case of ice and all, first it will come to liquid state. If we take ice and heat it, first it will come to liquid state, then it becomes vapor. But process of sublimation is that intermediate state is gone. Directly the solid particle is converted to gaseous form. There are particular compounds which show this property like the CO2 solid, the dry ice or even the camphor and even naphthalene balls. All those are the substances which shows the property of sublimation. So it is nothing but the transformation of solid state to directly the gaseous state. So we will see what is the change in enthalpy causing by sublimation. So sublimation is the direct conversion of a solid into its vapor form. Solid CO2 or dry ice sublimes at 195 Kelvin with sublimation value of 25.2 kilojoules per mole. So 1 mole of CO2 solid is converted to CO2 gas with absorbing energy of 25.2 kilojoules per mole. That's the concept of enthalpy of sublimation. So naphthalene sublimes slowly, and for this it needs sublimation energy of 73.0 kilojoules per mole. So in this case lesser energy was needed, so the sublimation was faster. In this case sublimation is slow because the energy required is more there. So what is actually the difference in energies or why this energy difference is happening? That we will see. So before that we have the definition, which is standard enthalpy of sublimation is the change in enthalpy when 1 mole of solid substance sublimes at constant temperature and a standard pressure. So under the standard conditions, how much energy is needed for sublimation, that is known as the enthalpy of sublimation. So the magnitude of enthalpy change depends on the strength of intermolecular interactions. That's what which we told just now, that the naphthalene is having more energy needed and CO2 needs less energy. All this energy change is because of the intermolecular interactions of that particular substance. The stronger hydrogen bonds are there in between water and they hold them tightly. But in case of organic liquids like acetone, intermolecular dipole-dipole interaction are weaker. In one case they have strong bonds, in this case we have weak bonds. So it requires less heat to vaporize 1 mole of acetone as it is having a weaker bond. In case of water, it is having stronger bond, and to vaporize that particular product we want more of energy. So energy requirement for this phase conformation is dependent on the particular substance. In this case we have compared water with an organic liquid. Whatever it is, the phase transformation is dependent, or the energy for the phase transformation is depending on the intermolecular attraction in that substance. So with this we complete our today's class. So please go through the concepts and prepare notes. Thank you.